And a step further from the LDA, in order to have good approximations for the exchange and correlation energy, is what's called the generalized gradient approximation, or it's also called GGA. Well, actually, it's a logical step in the sense that the local density approximation is taken as a reference the uniform electron gas, and basically what's doing is substituting the constant density you have in the uniform electron gas with the actual density you have at each point. So here, first, with besides including the information of the density, you also want to include how the density changes from one point to the other. And the next step would be just doing a gradient expansion of this uniform electron gas exchange and correlation Hall. So um, as I've said here, the next logical step beyond the LDA that was initially proposed was doing what's called the gradient expansion approximation, or also called the GEA, which actually is not the generalized gradient approximation, the GGA, as we'll see later the difference between the two. So one way of deriving that GEA is to start from the uniform electron gas, introduce a quick and slowly varying external potential, and expand the exchange and correlation energy in terms of the energy, of course, in the density, of course, and the gradients of the density. And up to second order, the expansion you can have for the exchange and correlation energy within that approximation, the GEA approximation, will be just this one, where here you have the exchange and correlation Hall for the local density approximation, which is coming from the uniform electron gas. This is the exchange and correlation Hall per particle times the density. So here, this interval here will be just the local density approximation. And besides that, you're multiplying that with this factor here, which is 1, and multiplying with 1, you are recovering somehow the LDA, and you're including another factor here, which is coming from the gradient expansion of the LDA. And the gradient expansion of the LDA, it will have this form here. Here I'm using this factor. Basically, you have an expansion coming from the gradient, but you're using that factor because this is basically a dimensionless quantity here. So that constant can be considered as a fitting constant, so that you can fit that constant in order to repeat, in order to have some or recover some property of the system that you want to describe. So here, that dimensionless quantity basically is the modulus of the gradient of the density over 2 times Kf. Of course, the Kf, as it depends on the density, and the density depends from one point to the other, it will also depend on the position vector, times the density that depends also on the position vector. So this is what's called, it's a dimensionless quantity, which is called the S function, which actually it's also giving to you information on the how fast. It's been a dimensionless quantity. It's giving to you information on how fast or how big the gradient of the system is. So that will be like the first proposal. That was the first proposal for the gradient expansion of the LDA. But actually, what happens here, in principle, it was they thought that it should work better than the LDA, but for real systems, this approximation here, the GEA approximation, turns out to be worse than the LDA. And why is that worse than the LDA? The source of this, of the GEA being so bad approximation, was found to be caused by the violation of the basic rules that associated to any approximation, which basically is this kind of exchange and correlation Hall does not satisfy the following rules: that the correlation, the integration of the correlation Hall over the whole space should be 0. It's not satisfied in this rule, and also that the exchange Hall should be negative. So these sum rules are not satisfied by this expansion. So this expansion is made, but without considering the sum rules here, which are not satisfied. So that's why this gradient expansion approximation, it was not successful. So what was the next step? Because in principle it looked reasonable that a gradient expansion should be better than the LDA approximation. So what was the next step? The next step was basically this one, the generalized gradient approximation. So they found an appropriate way to make this gradient expansion to work. How? So the failure of this approximation, the GEA approximation, led to the development of what's called the generalized gradient approximation, the GGA. And the exchange and correlation energy within the GGA can be written in generally in this way. It's going to be an integral of the function that depends on the density and depends on the gradient of the density. That's why we're just considering the first order gradient of the density. But now we are going to make an expansion so that they preserve the desired sum rules for the exchange and correlation holes. So the GGAs usually are built in the sense with real space cutoffs of the previous approximation, of the GEA's approximation, in order to include only those contributions from GEA exchange hole that are negative. So just contributions of the holes of the GEA holes that are negative, and truncate the resulting hole at the first distance, which satisfies the sum rule. So they truncate somewhere at one point when at the distance where it already satisfies the sum rule and make it 0 from that value on, from that cutoff value on. Therefore, of course, that even though simply throwing away these positive contributions to the exchange hole, because actually the exchange hole has to be negative, so throwing away, make it 0, where the exchange hole within the GEA approximation is positive. So we're making it 0. Of course, it looks very ugly in real space. So the resulting holes you're getting within these GGA approximations are going to be really ugly. But remember, the important thing is not how the exchange hole are going to, how they look actually, but the important quantity is the average of the exchange and correlation hole. And if this average of the exchange correlation hole are satisfies interesting rules and they look pretty much nicer, they are the key quantities, the average are the key quantities in order to have good exchange and correlation energies. So that's basically how these generalized gradient approximations are built, considering the gradient expansion approximations in terms of the gradients. And of course, the way of doing that, the way of introducing these cutoffs and the way of building the GGA approximation in terms of the GEA approximation is very different. There are different parametrizations of the GGAs, actually as there were different parametrizations of the LDA approximation. Here, I'm just going to show you one of these parametrizations, one of these implementations, which probably can be considered like the most used approximation because it's quite simple and it's given to you quite reasonable and good results. And it's the one which is called the Perdue-Burke-Ehrnhardt approximation, or just reduced to PBE approximation for the GGA. And actually these names are coming from the authors of this reference here, where they presented that implementation. They are Perdue, Burke, and Ehrnhardt in this reference. You can see all the details of this implementation, there's reference here. But basically what they did is just they split it, decomposed the exchange and correlation energy in two terms as usual, the exchange energy and the correlation energy. And here we have the implementation for the exchange energy, and here on the right hand you have the implementation they proposed for the correlation energy, which is a bit more complex than the one for the exchange energy. Here they wrote the exchange implement or the exchange energy within this implementation for the GGA in this way. You have that will be the exchange energy for the uniform electron gas as a function of the density. Actually, it's going to be this is actually the LDA approximation. This is the exchange energy per particle, of course, times the density times some enhancement function, which depends on the S parameter we defined before, which is the modulus of the gradient over 2 times kf times n. And this function, the parameterization they consider within the PBA parameterization for this enhancement function is basically this one here. I've said before in terms of this adimensionless function, which is the S function we have here. Okay, that's the parameterization for the implementation for the exchange energy. And here on the right we have the one for the correlation energy, where they wrote the correlation energy for the GGA in this way. Again, this is the density, and that's the correlation energy for the uniform electron gas as a function of the density, plus some function that was going to give you the gradient correction to this correlation energy. And the implementation of this H function is going to depend on the RS parameter, which is the average interelectronic distance, which of course depends on the density, and T, where T is this function against the dimensionless quantity, very similar to the S, but in this case, instead of Kf, you have here a Ks, where here is the Ks, which is related with the Kf vector. Okay, and here that's the function you have for that the implementation of the PBE for the H function here, which depends on some constants, as you can see here, alpha and beta and constants, and also A here, and the values of the A, alpha, and beta are given here. Of course, if you want more details, you can go to the reference here and see how they derived that implementation. So basically here we have gone a step farther from the LDA, and you have included besides the density at each point, we have included the gradient of the density on each point, and that's done in this GGA approximation, which is the generalized gradient approximation. That is a gradient based on the gradient expansion of the LDA, but making it satisfy the important sum rules on the exchange and correlation Hors.